So those who are online, please welcome to our presentation today, our class, which is, as you can see, it's instrumentation. And under that, we're going to look at measurement standards. We're going to look at sensors. We're also going to look at transducers. So you can be able to remember from our previous discussion, for those who are there, we were able to learn about the features. We're able to look at the measurement system. And under the measurement system, we're able to learn about the different process of doing a measurement, right from the detection of a signal until that signal is presented in a manner that it can be measured, or it can be presented to the final user. The variable conversion elements, the manipulation elements. We're also able to look at the static features of measurement instruments. We looked at errors. We're able to look at sensitivity, repeatability, resolution. So today we want to continue with that discussion by looking at standards. So first of all, we want to understand what are standards. And we want to say that standards are, so measurements are based on the comparison to some known quantity, or what you call reference. So measurements are not just a relative, but they're usually compared to some standards. So that reference is what you're calling a standard. And usually it is defined by the International Organization for Standards, ISO. And we have different types of standards which you want to mention. The first one being the international standards, the primary standards, the secondary standard, and also what you call the working standards. So if we look at the international standards, this is where we usually obtain our SI units. SI units can be basic or derived. And we know all the basic and the derived units you can see here. We have the meter, the kilogram, the candela, the mole, the Kelvin, the ampere for current, and seconds for time. And so these ones are usually defined by the International Organization of Standards, the ISO. For instance, when you talk about a kilogram, which is the SI unit of mass, it is usually a particular mass of platinum iridium alloy, which is kept somewhere in Paris. So a prototype of that, it is now what is usually taken out by different countries and countries to be used. So these artifacts, platinum iridium alloy, it has been used to standardize what you are calling a kilogram. However, this has been discontinued somewhere in 2019, whereby there's a new definition of a kilogram in terms of light and also the Planck's constant. Then you also have another one like the meter. The meter is usually defined as the length which is traveled by light in 1 over this value given here over second. So this is now what you call the international standards, where scientists or representatives from different countries, they form a body which from time to time, like after 4 years, they are able to redefine, or they're able to look at the international standards and maybe be able to redefine them ostensibly for purposes of increasing the accuracy of those standards. Then we talk about what you call a primary standard. A primary standard now is a measurement that is used in the calibration of what you call working standards. So a primary standard, as you have seen, it is now what countries are able to obtain from the international standard. It is usually now what is used to obtain other standards within a particular country or region. So so all these what you're talking about here is what you're calling a primary standard. As you have said, it is chosen owing to its accuracy and stability. it is a replica of what is kept now in the international laboratories. So a primary standard can be measured in terms of metrics, including the length, the time, or the mass. So a primary standard, basically, it's now the standard which is a replica of the international standard and is usually kept at the national level or a region. Then we have what you call a secondary standard. So a secondary standard, it's usually now what is compared periodically to the primary standard, depending on the accuracy which is required. These standards are not usually used in measurements, but they are used to transfer what you're calling standards, like to move a unit of measurement from the primary standard to the working standard. The working standard is now what is mainly used in the laboratories for calibration purposes for instruments in the lab. So a secondary standard just transfers accuracy from the primary standard to the working standard. So these ones are what you're calling the primary, the secondary standard, and the working standard. They're usually kept in a very safe place, and they're usually or periodically calibrated with the international standards to just ensure that the measurements which are kept, which you're going to get in the lab, they are of the highest quality possible. There are various areas, especially for you engineers, where you really require very, very high accuracy when you're doing your measurements. So that is why there is need for standardization. And now we look at what we call a working standard. A working standard basically is a device which is used to maintain the unit of measurement for routine calibration and certification work on a test instrument. So you get that in an industry or in a factory, there must be a working standard, which usually kept separate from the other instruments, and it is main use is for calibration purposes. So it is used after it has been calibrated, it goes for a period of like 4 years. So that means there's what you call certification. After that, then it is used to calibrate the instruments. Once they have been used for some time, you know that measurement instruments, they deviate from now what you're calling the true reading given by the working standard. So that is why they need to be calibrated from time to time. Calibration is just that process of measuring the output of an instrument or a measurement with what you're calling the working standard. So you can be able to see that they are usually kept separate in an organization setup, and they are usually reserved for the calibration purpose. So what is calibration? Calibration basically is the process of comparison of a measurement instrument to what we call the standard, to bring the instrument into agreement to an established standard. So when you're doing calibration, we are just checking the accuracy of a measurement instrument, which will depend on these 3 factors here. Number 1 is the time it was last calibrated. For instance, if the calibration requirement is that after 4 years, calibration again is done. So if you get that a working standard was calibrated 10 years ago, then it is obsolete and it cannot be depended upon. Then you have the difference between the calibration temperature and the operating temperature. So, and also we have the uncertainty of the standard used for calibration. So those are the factors which will determine the accuracy of an instrument, because an instrument cannot be more accurate than it is working standard. And it also depends, because you know the temperature is a factor which affects the sensitivity of instruments. Now, having looked at the different types of standards which we have, we again revisit sensors and transducers. Basically, you can define a sensor as an instrument or a device which converts the physical parameter, like these ones here, into a signal which can be measured mostly electrically. So it converts all these other physical parameters and it gives an equivalent electrical signal. At the same time, a transducer converts one form of energy into another. So it can be able to convert like like you can be able to see this diagram here. We have one form of energy. It can be mechanical, it can be heat, it can be sound. And then so the transducer can be able to convert that into an electrical energy. So most of the instruments which we have, they act as both sensors and transducers. That means they can be able to sense, they can be able to give the electrical equivalent, and they can be able to convert it to another form of energy. So sometimes the words transducers and sensors can be used interchangeably, owing to the fact that transducers can also have sensors within themselves. So we're going to look at some of these transducers or sensors. And the first category is what you're calling displacement, position, and proximity sensors. So these ones are able to convert displacement into an electrical equivalent. So examples like potentiometer, strain gauge element, capacitive elements, differential transformers, and all these others which we have been able to mention here. So we have an example here of a potentiometer sensor. This one here, it is able to change displacement. It's able to change displacement, either linear or what you call angular, into what you call, you can be able to see now, there's a sensor here, what you're calling a potentiometer, which is able to change the change in displacement into an equivalent electrical output. So this one basically converts displacement into an electrical signal. It has a resistive element and also what you call a sliding contact. So we're going to look at how this one works, especially the electrical part. Now, the one which is able to convert into an electrical signal. So first of all here, so we have a displacement. Maybe some force has been applied, and so there's a change in displacement. How is that change in displacement? You can be able to see here the direction of rotation. There are some threads here which are able to either tighten more or loosen depending on the force which has been applied. And how now there's a coil spring here, how that one is converted. So we want to look at especially the potentiometer part. The potentiometer part, it has what you call, it has a voltage applied to it, a voltage source, and then it has a resistance element here at point A and at point B, where now the output voltage is going to be tapped. So the change in displacement is going to be converted into a voltage output. And so we are going to use some bit of Ohm's law, whereby voltage is given by current multiplied by resistance. But current is given by voltage across the source divided by the total resistance. So the resistance at point A and the resistance at point B. So when there is no change in displacement, this is the value which should be read should be the value of the voltage of the source here. Now, the voltage, that is the output voltage, will therefore be given by, from here now, since you have defined current, it will be equal to the whole of this multiplied by resistance. So we have the output voltage, which is going to be read, will be given by all these. But you can see from this equation here, there is no displacement being mentioned anywhere. It is just a relationship between the output voltage and some resistance here between point A and point B. So there's another formula for resistivity, which is now able to bring in the issue of length. And the formula is that resistance is equals to resistivity multiplied by length divided by the cross-sectional area. So if we make, if we can be able now to substitute this value of resistance at this point here, the resistance here, then our formula now becomes the voltage, the output voltage will be equal to the voltage across the source multiplied by the length A divided by, so this formula now here brings in divided by the length at point A plus the length at point B. So what you're going to have here, as you can see, is a relationship between the output voltage and the length or the displacement. So any change in displacement will be able to result into a change in output voltage. We have some applications of potentiometers here. They are used on machine tool controls, elevators, forklift trucks, and all these which have been mentioned here. Molding machines. They are used in computer-controlled monitoring of sports equipment. So all these are some of the areas where they are also able to be applied, basically to change the change in displacement to be able to give an output voltage based on the Ohm's law. Then we also have some sensors which can be able to measure velocity. So these ones are changing velocity into some kind of an electrical equivalent. And we have one of them here. We have what we call a tacho generator. So a tacho generator is used to measure angular velocity. And you can be able to see here, we have a toothed wheel, which is able to rotate. And as it is rotating here, you can be able to see besides it, we can be able to see a coil whose terminals now is connected to the output. So a pickup coil is wound on a permanent magnet. So as the wheel is rotating, the air gap, so you can be able to see the gap between the wheel and the coil, the air gap between the coil and the ferromagnetic material changes. And I think that is the key thing here. So the greater the speed, the greater the difference in what you're calling the air gap between them here will keep on changing. So you can be able to see this air gap. If the velocity is 0, the air gap is what we have here. But the more this one the velocity increases, the air gap is going to decrease. And that one is going to change what we call the magnetic flux. So as the magnetic flux also changes, then magnetic flux is what is going to induce an EMF. So an output will be given out, which is in terms of voltage. So there's a change in velocity. That change in velocity changes the what you call the air gap here, and that one is going to change what you call the flux, which is going to be linked in this coil, and so that flux will be able to produce an EMF at the pickup coil. So that is also an example of how you see what you have is velocity, which is a kind of kinetic energy, but that kinetic energy is now converted into an electrical energy. So this can be a sensor and a transducer at the same time. Then we have what we call a force sensor or a strain gauge. This one is able to change force into some kind of electrical form like resistance. So force is applied here, and then it has what we call some strain gauges, which are going to change. So a strain gauge is a kind of spring-like material, which is able to, as the force is applied, then the strain gauge is going to be under some kind of compression, and that compression or relaxation is going to be converted into an electrical signal. So the arrangement for measuring the force is generally referred to as what you call the load cell. The load cell is a cylindrical tube which strain gauges have been attached. When force is applied to the cylinder, the resistance will change, which is a measure of the applied force. So here, a change in the resistance will be proportional to the applied force. So this is now the electrical working of that bit. We have a diagram of a Wheatstone bridge. This one here consists of, you can be able to see 4 resistors. And that, you can be able to see a group of 4 resistors which have been arranged. And then there is an output voltage here. We have an external voltage. And then there is the output voltage on this side. So if all the resistors are balanced, meaning that the ratio of R1 to R2 is equals to R3 to R4. So when the potential difference on this side and this side are balanced, then the output, which will be tapped from these ends, will be reading 0. That means the potential on either side is actually balanced. But if there's a change in the value of one of the resistors, then there will be an output voltage, which will be interpreted using Ohm's law. So basically, this Wheatstone bridge now will be able to will be equivalent to the strain gauges which are placed inside our load cell, so that when force is exerted, then there's going to be some change in the output voltage. So these are just some diagrams trying to explain more about that. Load is applied on this end, and then we have a strain gauge. These are strain gauges, and you can be able to see the way they have been arranged. So we have like resistor 1, 2, 3, and 4. So when force is applied, some of them are going to be under compression, others are going to be under kind of they will stretch. So these are the ones which are here. Some of them are placed horizontally, others vertically. So force is applied here, but what you're going to see as an output is basically a change in voltage. So the output voltage will be given by this formula here, minus that, multiplied by this is the external voltage. Usually they have to be powered for them to be able to measure a reading. So remember, we have some type of active transducers and passive transducers. Active transducers, they have to be powered externally. So in a load cell, the resistors are replaced by what we call a strain gauge. So we have what you call a strain gauge here. So instead of a resistor here, we have a strain gauge, which, for example, this one is under compression, and this one is under compression. This one is under tension, this one is under some kind of tension. So these two are going to be under compression, and these other two are going to be under tension. And so this is how, like, maybe a load cell or that bridge sensor is arranged. So force is applied at this particular point here. So some of them will be under compression, and be able to see here T, they are under tension, tension here, tension. This one is under compression, this one is under compression. And so that kind of arrangement is what is going to give an output voltage according to this formula which we've been able to mention here. So there's a force which is applied, but what do we get as the output? It is a voltage. So when there is no force applied at all, the output voltage will be 0. But as force is applied, then as you have indicated, some of these strain gauges, they're going to be under compression, others are going to be under tension, and that is going to produce an output voltage. Another one is the linear variable differential transformer. This one is also, we had mentioned earlier, this one will be able to change displacement into a voltage. So you can see it's a linear variable differential transformer. This is how it looks like. It has, but what is important, it has some coils here. It has a primary coil, and it also has a secondary coil. So it has a displacement with an input range between 2 to 400 millimeters. So that is just to show that it's going to change displacement into some kind of voltage. So we want to understand it. It has a primary coil and some secondary coil. The secondary coils are wound in such a way that they are opposite each other. They are opposite each other, such that when there is no load or there is no armature here which is moving, then the output voltage is actually equal to 0. So the central coil is the primary coil, and the other two are the secondary coils. This one here and this one over here. The secondary coils are connected in series in such a way that the output opposes each other. So it's just the winding. One could be wound clockwise, the other one anti-clockwise, and they are equal magnitude so that the output becomes 0. Then a magnetic core is attached to the element of which displacement is to be monitored, and it is placed inside the insulated tube. So this is a magnetic core, and onto which here now it's attached to the displacement to the material which is causing displacement. So on one side here, you can be able to see when it is moved, for instance, to the upper side. When it's moved in that kind of side, then we want to have a change in magnetic flux linkage. Let's look at that explanation there. When the magnetic core is centrally placed with its half portion in each of the secondary coil regions, then the resultant voltage becomes 0. But if the core is displaced from the central position more into the secondary coil, then we want to have more EMF is generated in one coil than the other. So in our diagram here, when it is displaced upward here, remember the principle behind the induced EMF is that there must be some relative motion. So if it moves towards this direction, there's going to be more EMF being induced in this coil than this one here. So that means the output voltage will not be equal to 0. Similarly, when it is going to be moved downwards here on the lower side, there's going to be a magnetic flux linkage, which is going to induce more EMF in this coil than this one here. And again, that means the output voltage is not going to be equal to 0, but at least now that a reading will be given out. So when there's relative movement, whether upwards or downwards, there's going to be an induced EMF, which is now going to translate that displacement into a voltage. So the magnetic core is further displaced, the value of the resultant voltage increases in proportion with the displacement. So with some help of signal processing devices such as filters and the demodulators, then the precise displacement can be measured using an LVDT. These are the applications of the LVDT sensors. They're used to control weight and thickness. The LVDT, they're usually placed at the meter breaches or the weigh breaches, and they're able to measure maybe the weight which is being carried by a particular load. And that one usually just happens by the physics which I've explained there about changing magnetic flux, which will be able to use an EMF, and a proportional output voltage is going to be read. So we just have an example here on how you can be able to calculate some of the static features which we discussed. I have an example here. This is what I was able to have. We have an LVDT, which is connected to a 4-volt voltmeter. So this the voltmeter is going to give us the output voltage through an amplifier whose amplification factor is 500. So remember, signal manipulation, maybe the displacement could be, the changes in displacement could not be big enough to be read out. So you need an amplifier to amplify that displacement. So an output of 1.8 millivolt appears across the terminals of the LVDT when the core moves through a distance of 0.6 millimeters. If the millivoltmeter scale has 100 divisions and the scale can read a quarter of a division, calculate the sensitivity of the LVDT and the resolution of the instrument in millimeters. So we are going to look at, first of all, the sensitivity. Sensitivity is a measure of the output voltage to the displacement. Remember, we had defined sensitivity in our earlier discussions. So the output voltage is actually 1.8 millivolts, and the input voltage, or the change in displacement, is 0.6 millimeters. So therefore, our displacement, or our sensitivity rather, will be equal to 3 millivolts per millimeter. That is the sensitivity. What about the resolution? So resolution, you're going to see, we were able to say it's like the smallest change in the input which can be measured, the measurable change which can be measured. And we're going to obtain that by, first of all, taking this, getting the sensitivity of the measurement. The sensitivity of the measurement will be the amplification factor times the sensitivity of the LVDT, which you have obtained to be 3 on this end. So That 3 multiplied by 500 will be amplified to 1,500 millivolts per millimeter. So that is the sensitivity of the measurements. And then, because now this is a measurement system, it has several measurement parts. So therefore, this 1,500 will be the sensitivity of the measurements. And then the minimum voltage, which can be read by the voltmeter, it is a quarter of the full scale deflection, which is given as 40. So it has if you can be able to check here, it's a quarter of a division. So a quarter of our division here, the voltmeter, it has 100 divisions. So I'll check out here the 40 where I got it from. An output of 1.8 millivolt appears across the terminal. So when the core moves through a distance of 0.6 millimeters. So I'm just trying to get these 40 divisions. What do they represent? So we have 100 divisions, and the scale can read a quarter of a division. So a quarter of that, let me see, an output of 1.8 millivolts is going to be that. So I'm just trying to get where I got this my 40 from in a short while. So a quarter of 40 will be equal to 10 millivolts. So to get the resolution, we'll divide by 10. Let me see. 10 divided by the sensitivity of the measurement, which is 1500, to give us the value which has been given here. So if we can be able to check, I was just trying to explain this. I'm sure somebody is going to ask about this. So we have 100 divisions, and these divisions, they represent, let me see, 1.8. So I don't know if we can be able to divide 100 divided by 1.8. I'm trying to check where I got the 40 from. One scale division, it is 4 over 100. Good. So we have 4 folds on this side here, and then we have a total of 100 divisions. So therefore, to be able to get one scale division, it will be 4 divided by 100, which will be equivalent to 0.04, which is the same as 40 millivolts. So therefore, a quarter of that 40 is what we get as 10 millivolts. So basically, that is what I was able to prepare for today. I should have given some more questions on this. Maybe I'll be able to send some. Also try to check on this. But just a quick review of what you've discussed. Today we have looked at standards, where we have said that actually for engineers, you must be able to understand that, especially if you're out there in the field and you come up with a particular device, a measurement device, then there's some protocol for you to be able, for that one to be able to be acceptable. So that kind of protocol, first of all, we are trying to get a full picture of how standards we get them from. And in summary, you have said we have 4 main types of standards, from the international level up to the lab, where we have what you call a working standard. And most of these standards, they are governed by the international body of Organization of Standards. And so we said something about calibration, where we said constantly these instruments which are used in a particular lab or a particular industry or a particular factory, they continuously have to be compared to the working standard. The working standard, after some time, usually 4 years, it has to be compared to the primary standard. So the primary standard is a standard which is kept at the national laboratories. Like maybe here in Kenya, we have the CABs. So it has to be calibrated. And the calibration, its main aim is to check on accuracy, which depends on time, temperature, and certainty of the standard used. Because even these standards, they also have their standards which are contained in the certification with which they come with. Then from there, we have looked at sensors. We have also looked at transducers. A transducer, for instance, is able to convert one form of energy into another. And mainly, for measurement systems, it is electrical form of energy. So the electrical form of energy can be inductive, like we have seen. It can be capacitive, it can be resistive. Then from there, we have looked at some examples of sensors and the transducers. And we have said that if you have an instrument which can be able to do the work of measurement or sensing, and then it also converts that form of energy, then we can use the term transducer. We have looked at some of them. The potentiometer, it changes displacement into a voltage, an output voltage using Ohm's law. We're able to explain this one here. Then we have been able to look at a tacho generator, which is able to change velocity into, again, an output voltage in the form of EMF. And this one here now uses what you call some change in inductance of this coil here, as the velocity is able to change the gap between the two, the air gap. Then you have also looked at the strain gauge, or what you call the load cell, which works similar to a Wheatstone bridge, but where the resistors here, they are replaced by what you call strain gauge. So the strain gauge, some of it is going to be under compression, others under tension, and they are able to convert it into an output voltage. Lastly, you have also looked at an LVDT, the linear variable differential transformer, which also is able to convert displacement into a kind of voltage. And you have tried to explain how that one takes place by using this primary coil and the secondary coil, and how the transferred, what you call the EMF which is being transferred will be different depending on the amount of what you call the flux linkage. So there's usually flux linkage between the primary coil and the secondary coil, and that flux linkage can be affected depending on the position or the movement of the armature here. So if it gets displaced towards one side or the other side, in whichever side is going to move, there's going to be a change in the flux linkage. And remember from some basic physics, when we have a flux linkage, it translates into an EMF, and that EMF is also going to give us an output voltage. We have also looked at one example here, and I believe we'll be able to get some more examples, especially to now check on sensitivity, resolution, and things to do with errors. That is the presentation I was able to prepare for today. And I'm going to maybe allow